Let us start this lecture with a thought process from Albert Einstein, who says there are only two ways to live your life. One is as though nothing is a miracle, that most of us think. Like other is as though everything is a miracle, that you enjoy the life, right? And that is our scripture always talk about that, right? But we do not follow it, unfortunately, and getting into depression and other problems, right, in modern time. So, let us look at what we learnt in the last lecture. Basically, if you look at, we looked at the various regimes of turbulent flame, premixed flame. One is of course the weak turbulence flame, right. Other is wrinkled laminar flame, the flamelet in eddies, and distributed reaction kind of things, right. We looked at the various kind of non-dimensional parameters, right, Reynolds number, and then Damcolor number, and then root mean square velocity ratio, and all scale ratios, right, L naught by delta L, Lk by delta L, all those things we have looked at, and looked at a Voorhees diagram. And if you look at, we basically discuss about the distributed reaction zone, which occurs in the low Reynolds number and low Damcolor number. But that is very difficult to establish. However, one can establish using a stirred reactor. Stirred means you will have to give some jets like various directions and put together, and you do that. Now, we will be looking at the turbulent burning velocity, because as I had told earlier that laminar burning velocity is very fundamental to the premixed flame. Why? Because the all other parameters like minimum ignition energy, quenching distance, and then your flammability limits and other things will be related to the laminar burning velocity, including flame thickness. So, similarly, turbulent burning velocity is very important, but it is not that easy how to define it, because of fact that turbulent burning velocity, it depends on the characteristics of the fluid flow, right, and velocity at which unburned mixture enter the flame zone normal to the flame, because the surface is so convoluted that which one you will take as surface, each zone it will be corrugated or a different. So, that is also very difficult, and that is why it is very difficult to measure the velocity of unburned gas near the turbulent flame, and then we will be looking at some average sense, right. That is why it is difficult to measure the way we did in the laminar burning velocity. So, that is St is equal to, what we will be talking about is St is equal to m dot is nothing but reactant flow rate into rho u is the density of unburned mixture, and A dash is the time average of flame surface, right. The flame surface will be changing, right, okay, with respect to time. So, if you look at the flame surface will be changing, it need not to be so regular, right, it will be, this is your flame surface, right. If I take one dimensional flame, right, flame surface, which is with respect to time, right, and this is at one instant of time, there might be another instant of time which you can be like another one, this is with respect to time, right. So, at different instant of, sorry, this is, oh I am sorry, this is with respect to x, but this is the 2 instant of time, t is equal to t 1, and this is corresponding to t is equal to t 2, 2 instant I am talking, that will be changing, we have already seen. So, then you will have to take average over the time, and then you will consider that A dash, right, and which is need not to be really one dimensional in nature also. So, therefore, we will define that way, and we will be trying to get expression for that. For that matter, what we will be doing, we will be considering the weak turbulent flame regimes, right, where the extension of laminar flame, and that means the flame will be basically similar to laminar, because that low turbulence will be there. The flame surface will be looking to be smooth, it will not be affecting that much, and turbulence scale is order of laminar flame thickness, that is delta L, right. Of course, the ST will be greater than SL, which is expected. I am like, we will see how it is, right. And this is because of fact that with increase in thermal diffusion, that we will see. We have seen basically we know that SL, this is derived from very simple relationship. We have seen that SL is basically proportional to root over alpha by R. What is that? RR is reaction rate, right. You can say m dot triple dash F average, right. And similarly, we can define, right, SL is ST is proportional to alpha T RR, right. If I will assume that the reaction rate is not affected by the turbulence, okay, that means reaction rate will be remaining same for both the laminar and turbulent, I can arrive at that ST by SL alpha T divided by alpha L, okay, I am saying alpha L means thermal alpha is the thermal diffusivity, this is thermal diffusivity, right. And now if you look at for the, if I consider the Prandtl number as same for laminar and turbulent, right, which need not to, but if I will consider that, we know this Prandtl number is equal to nu by alpha, right, and if I say it is for turbulent and this will be for turbulent, and similarly if I say this is laminar, like L by alpha L, and if I consider that Prandtl number is basically same, that means Prandtl number T is equal to Prandtl number of laminar, then what will happen? I can write down the ST by SL is basically about ST by SL is equal to, I can write down nu by T by nu of alpha 0.5. For laminar, for pi flow, we know for pi flow we know that is nu T by nu is equal to 0.01 RE, right. So, then if I will say this is equation 1 and then substitute these values in equation 1, and I will get ST by SL is equal to 0.1 root over RE. So, this is a relationship you can get basically from the phenomenological analysis, that turbulent burning velocity is proportional to the laminar burning velocity and depends on the Reynolds number, right. But keep in mind that this is having limitation, right. What is the limitation? That is, if this alpha T or the nu T is 0, there is no turbulence, right, then what will happen? That turbulent velocity will be 0, right. If Reynolds number is not there, is very very small, right, it will not, or in other words, if I look at this expression, there will be some kind of a limitation, right. And that is nu T, right, tending towards 0, ST will be tending towards 0, right. Of course, when you put this Reynolds number, this will not be rho V d by nu, like nu-T 0, then this will be very what you call Reynolds number very high, it will be very kind of having no meaning. So, that has to be looked at it, and that is the limitation of this model, right. So, let us look at some experimental data ST by SL versus the Reynolds number. You can see that with certain Reynolds number, let us say that around maybe 2300, right. This is RE is equal to 2300, that ST and SL is not changing, it is remaining almost constant, but afterwards it changes, right, with the power to the 0.5 you can say, or around that, it need not to be 0.5, it may be something. So, it is kind of thing, but once it is in this regime, that we call it as a weak turbulence regime, right. This is weak turbulence regime, right. But here of course it is different, these are the experimental means it became almost linearly increasing, this is a parabolic in shape kind of thing, right. So, this is a simple relation we state that from this one can say that this is the relationship what we have derived is basically is matching or similar to the experimental data, these are all experimental data, right, kind of things. So, by this one can really determine the laminar turbulent burning velocity. There is another regime where the wrinkled laminar flame which will be occurring. So, in this case if your fuel plus oxidizer mixture is moving a certain velocity which is having some fluctuating velocities, and it may affect the flame, keep in mind that it will be distorting the flame, right. It will not be changing in the it will be not affecting the inside the flame thickness kind of thing. So, and that we call it as a wrinkled laminar flame. The flamelets in the flame surface propagates at some laminar burning velocity. So, if you look at locally, if you look at it will be moving with a laminar burning velocity, and turbulence causes only the wrinkling of the vessel, corrugated, make it corrugated, right, wrinkle, right, the surface. And that is of course which will occur when the Reynolds number and Damkohler root over is very large values, right. That means the length scale is much larger than the laminar burning thickness, flame thickness. So, turbulent burning velocity if you look at is given by, we can do a mass balance, that is rho u, A star, A dash is the average velocity. I mean if you take all those things with respect to time and average, you may get something which I have shown here, like into ST with which this will be moving, right. This is just a hypothetical thing, it is moving with ST, right, and into rho u and AWSL, AW is the wrinkle area, surface area, right, into SL which will be moving, right. So, then from this I can cancel it out, right, and this is basically ST by SL is equal to AW by A average. And according to Damkohler, the constant laminar burning velocities, right, can be as the AFL, right, it is the flamelet surface area divided by A average, if I take this is average velocity, right, VU by SL. VU is the velocity with which it will be, the fluid will be moving, right, in this case. And in the similar way, I can also find out turbulent velocities like related into AW, that is the wrinkle laminar divided by A average is nothing but because the wrinkling is occurring due to V dash RMS values, right, into SL. So, we know that AW A, this is AFL, right, I can write down here AFL, the flame surface is equal to basically A average plus AW, This is due to the this wrinkling surface that will be there, and this is the average which will be taking place, right. At that will be at any instant of a kind of thing it will be giving. So, therefore, I can write down S T by S L is nothing but your A F L divided by A dash, and this if you look at, I can write down as is equal to A F L by A is equal to that, and A F L is nothing but your A average plus A W divided A W is nothing but your 1 plus A W by A dash, and A W by A average is nothing but your B dash RMS by SL, right. And this is relationship is basically known as the Damkohler relationship, right, which is and keep in mind that when it will give a relation linear relationship, B dash RMS is 0, ST divided by SL is equal to 1, right. That is the thing, because if it is there is no turbulence, then naturally ST SL will be equal to 1, right. And but however, this does not really predict the experimental data. Then Klimov has talked about taken the experimental data and find out ST by SL is equal to 3.5 B dash RMS divided by SL power to the 0.7. Keep in mind that this is having a problem. Problem is that when V RMS is 0, that means ST by SL will be 0, right, and which is not true, because if turbulence is not there, right, that does not mean that laminar burning velocity will not be there, right. So, therefore, this is the limitation of this model, right. So, that is the limitation of this model, and then the Clavin and William has given another model, right, which is ST by SL is equal to 0.051 plus 1 plus 8 C V dash RMS square, and then the whole square of root over, then again root over of the entire thing, right. And if you expand this thing by in the Taylor series, you will get basically ST by SL, right, is equal to 1 plus C V RMS divided by SL whole square, right, that you will get. And keep in mind that this is possible only when that for small values of V RMS divided by SL, this is the valid one, right. So, this however, it is giving a some consistent value, V RMS is 0, this ST by SL is nothing but your equal to 1. That means that if turbulence is not there, laminar velocity and turbulent velocity is equal to same, right. That is consistent. And keep in mind, these are all little phenomenological analysis. You may find several relationships for the even for linked laminar burning velocities. Even you can get several relationships for turbulent velocity and laminar velocity ratio in this regime in literature. However, I am discussing these 3 of them, and if you look at the experimental data, you will find for SL is equal to 40 centimeter, which is corresponding to methane air, and phi is equal to 1, right, TU is 298 Kelvin, P is equal to 1 atmospheric pressure, right. You will find that this is changing according to Damkohler relationship, changing with respect to V dash divided by SL linearly, right. And these are all experimental data, and Klimov actually his data is matching well with the experimental data, right. And unfortunately, the Clavin and William does not match, I have not included, does not match with experimental. It may be little bit better than the Damkohler, but is still away from that, right. And this is about how to handle the turbulent burning velocity for wrinkled laminar flame. Let us look at distributed reaction zone, right, kind of regime, where what will be happening that this is the ADs which will be coming over here, right, and this regime, as I had told you earlier, that it is happening where like intensity, high intensities are of the wrinkling is there, and distinct regime for with a small pockets of reactants are formed, right. And you will get some kind of finger like structures, and you will get where this is a very turbulence level will be very high. As I told that it will be occurring in it will not be occurring in the practical devices kind of things. Till now nobody has designed such a device that where the turbulence level will be with the smaller Reynolds number, the turbulence will be higher, and but however the ADs will be smaller in size, right. This is your it is possible, of course, however in laboratory scale the stirred reactor, you can think of a reactor here, right. These are the jets, right, where the fuel can be coming over here. These are the jets with which the mixture will be coming, right, and these are impinging into a surface, right. So that what happened, the intense mixing will be taking place, and this is known as stirred reactor. It will be mixing. You can think of putting a fan and then moving it at a very high velocity, and you are mixing, that way. Are you getting? It is a very intense mixing is taking place. So that means scale will be very small, right, and this is a stirred reactor. Which will be taking place, but that is quite difficult, and I have already told you that this is in the Borghi diagram where Damköhler number less than unity and Reynolds number is very small, right, and quite difficult to occur in practical device. In laboratory such situation are created using a stirred reactor, I have already discussed, and chemical reactions are not completed in reaction zone, rather occur in the post flame region, because the mixing is so high that reaction will not be really taking place, that is another problem with this kind of things, right. Regime needs more understanding. However, people have given relationship ST is equal to 6.4 VRMS, that V average divided VRMS 3 power to. This is a semi empirical relation what is being used kind of things, right, which is of course meant only for the turbulent velocity, and when it will be 0, this VRMS, of course this will be, there will not be any turbulent velocity kind of things. So let us look at Flamelet in ADs, right, and according to the Borghi's diagram, this region between the upper bold line Lk by delta L equal to 1 and L naught by delta L, right, and this is the Flamelet ADs which will be taking place. And keep in mind that here what will be happening, that large ADs, large parcel of unburnt gases which will be entering into, this is your reaction zone, right, this is your reaction zone, and when it is entering into that, it will be undergoing kind of changing its shape and size. It will be, there will be like breaking down the ADs, and when it breaks down, it will be trying to mix with the hot gases, and its surface area will be increasing, right, and as a result the interfacial contact between the burnt and unburnt gases will be taking place. In some places it may extinguish, that means there will be some kind of a flame which will be, for example, there is a burning is taking place, right, here burning, right, and this is unburnt, right, unburnt. If it is unburnt, then what will happen? There will be some extinction region will be there. So as a result, the combustion is determined by the rate at which, right, the parcel of unburned gases are broken into smaller, right, a smaller one caused by the eddies, and that means the burning rate is governed by the turbulent mixing rate rather than the chemical reaction rate. So, that you will have to keep in mind, and this is basically as I told that parcels of unburned gases and fully burned gases you will be getting, right. And flame mass burning will be dependent on rho Cf, and that is basically concentration of fuel, right. No, sorry, Cf is a constant, right, Cf is a constant, Yf RMS dash is basically mass fraction, this is mass fraction of fuel, right, this is fluctuating mass fraction, right, mass fraction of fuel, and epsilon is your dissipation rate and Ke is the kinetic energy, right. And if you look at the Cf, which is a constant, right, this is a constant, it may vary 1 to 100, generally people above 10 that it is a little lower side, and as I told that the epsilon is basically the turbulent dissipation energy. If you look at turbulent dissipation energy, by definition we know this is nothing but your kinetic energy change in the time, and this kinetic energy we know that kinetic energy, turbulent kinetic energy is basically 3 by 2 V RMS square, and this is possible when this is for the isotropic turbulent flow, right. What do you mean by isotropic turbulent flow? That is Vx dash is equal to of course RMS, Vy RMS dash is equal to Vz RMS dash. It will be uniform, but that is not the case in most cases, but we have taken for this, right. And then I can say change in that is nothing but by 3 by 2 V RMS square, right, divided by change in basically if you look at this is nothing but integral scale by V RMS, right. And now if you look at this I want to find out what is this epsilon by Ket is nothing but your V RMS by L naught, isn't it? I am taking this is nothing but your Ket, right. You can say initially it is 0 and then that thing and then you are doing that. So, this is proportional that, then I can write down this m dot triple dash is basically rho f Yf dash RMS is equal nothing but V RMS dash divided by L naught. That means this mass fraction rate of the fuel, right, you can say that is the consumption per unit volume will be dependent on what? Dependent on the fluctuating velocity of the component of RMS velocity divided by the integral scale. So, that will dictate, and also the fluctuating mass fraction of the fuel, right. So, it will be the reaction rate will be basically not calculated from the Arrhenius, from the turbulence, right. Wherever there will be mixing, so it will be getting consumed because the reaction is very fast here as compared to the your mixing time, right. So, this is the thing which is being used for the eddies, and we can really use this for finding out the burning velocities and other things. So, with this I will stop over, and in the let us look at this kind of flamelet in eddies occurs in spark ignition engine and premixed burner and also the high voltage burner, high velocity burners. and with this we will stop over. In the next lecture we will be discussing about basically diffusion flame, right. Thank you very much.